So, in order to understand a little bit about the atom and how it's related to chemistry, more than just the bonding stuff, which we'll get into later, we have to talk about light. So, first thing I want you to do is I want you to draw this little wave function. Just make a couple of waves going across your page. Pause the video so that you can do that. Good. So now a lot of the light stuff has to do more with physics than it has to do with chemistry. We're going to talk about the chemicals that are involved with it. So, but we have to talk about where the light comes from in the first place. So let's identify a couple of parts on this wave. So the first thing I want to do is identify a couple of parts in the wave. So hopefully most of this you will remember. So the top of the wave is called the crest. Not the Colgate, the crest. Yes, I know people always get confused a little bit. It's not the toothpaste, it's the top of the wave. Okay? The bottom of the wave is called the trough. And then the distance between two consecutive crests or troughs is what's called the wavelength. Okay? Now you'll notice that the wavelength is abbreviated with a lowercase lambda, and it kind of looks like an upside down Y. So the distance between any two consecutive crests or troughs is what is called the wavelength. And the last thing I want you to know is the frequency. And the frequency, was abbreviated with a little v, is the number of waves that pass a point in a given amount of time. It is going to always be a length divided by a time for the units. So typically it'll be in meters per second. Okay, so those are the parts of the wave the thing about the wave that I want you to know. Now let's talk about the electromagnetic spectrum. Now here's my thing. So you got this little drawing. I don't recommend writing this out. Now if you want to draw it and color it, and you're more than welcome to, but I really recommend just simply taking a screenshot of this or printing this out from the PowerPoint. So this is what's called the electromagnetic spectrum. So all of these are forms of radiation. Yes, I know. We think of radiation as being bad, and it's true. Radiation is bad. All of these are bad for us in some form or fashion. Now, what I want to do is spend just a couple minutes going over a couple of these key ones about where they're used and why they're important to us. Now, your one all the way on the left is your gamma rays. Gamma rays come from radioactive decay. And these are typically what we associate with things that are very bad. If you're exposed to radiation, you're exposed to gamma rays typically, and that's what causes cancer. Now, gamma rays, the most popular use of gamma rays was to create the Hulk. No, that's not possible. You cannot become big and green and muscular if you get exposed to radioactive decay. So gamma rays, very dangerous, causes cancer. X-rays. X-rays we know are used in the medical world. An X-ray works because it sends radiation through your body. It hits things that are dense like bone, and they bounce back. And it kind of works like a weird looking camera. So, and then everything else, anything it moves through becomes invisible on the screen. So that's why only your bones are visible. And that's how they can tell breaks or density or those kinds of things. UV, we know the UV comes from light, but hands down the most fun use of UV is black lights. Okay, it's ultraviolet light. It's below violet UV light. Now, the middle section we're going to talk about in a minute. Let's go through the other ones and we'll come back to visible. Now, on the far right is infrared. Infrared are usually like heat signatures. If you've ever watched the Predator movie, you've seen this before. The heat signature that pops up and it shows like hot spots are red, cool spots are blue. That's where infrared comes from. Radar and FM we know from like TV and radio waves and things of that nature. Radar, like as in sonar, things like that they send out radar waves and they come back and they bounce back. It's usually how we send signals back and forth between satellites and around to satellites and to around the world and to satellite dishes. Up here, up near TV, you have your microwaves. Microwaves are used to send long range communications. So those are sent to the farthest satellites. Also, we know microwaves in our houses. They use a microwave radiation that goes into the food and vibrates the water molecules specifically, and those water molecules get hot by friction, and that's how it heats up food. So now let's talk about our visible light. The visible light spectrum is the only portion of the spectrum of this whole electromagnetic spectrum that we can see with our eyes, meaning no special device. This is your Roy G. Biv. This is your rainbow effect. Reds have the longest wavelengths. Violets have the shortest wavelengths. Reds are the easiest to see. Violets are the hardest to see. You'll notice that violet is the smallest portion of the wavelengths. Now, do you need to know all these little numbers? No. You just need to know generally where they are, and we really want to only focus in on the visible. So know that visible goes from about 400 nanometers to 750 nanometers, and that will become important later in the marking period. You'll see for the quarterly. Okay, so visible light, notice that it's a very, very tiny portion of this overall spectrum. We cannot see anything else on this spectrum without using some sort of device to show it to us. Visible light is the only portion that's visible to the naked eye.